Hi, this video is going to describe the C++ code we could use to implement the binary search tree removal algorithm from the previous video. That last video described this algorithm in terms of pseudocode. This video describes it in terms of real working C++ code. The video here builds directly on that previous video describing the binary search tree removal algorithm. It also builds on the earlier video that described our binary search tree class and binary search tree node class. So if you're not familiar with those videos, definitely watch those before tackling this one because this one builds on that stuff. This video won't make sense if you're not familiar with that content. So what we're going to do is go through the same operations that were in the binary search tree algorithm video that presented pseudocode one step at a time. We're going to go through the same sequence of operations but present C++ functions for each one of them. So we're going to start with the highest level public function. Each one of these functions calls another helper function, so we're going to kind of go down that chain of helper functions starting at the highest level and working our way down to the more low level, more detailed functions. To begin with, this goes in our BST template class. K is the key type, V is the value type. This would be the one and only public function in this video, bool erase. So erase is given a reference to a key. The job of erase is to make sure that key is not in the tree. And there's two ways that could go. If the key is not actually in the tree already, then erase doesn't do anything and it returns false. It doesn't throw an exception, it just does nothing and returns false. But if the key is in the tree, then erase takes it out of the tree and returns true to say that we did just change the tree. So we implement that with an if statement. We say if not contains key, return false, and that ends the function call right there. Contains is a public member function we defined earlier that takes a key and returns true if the tree has the key and false otherwise. So this does that search starting at the top, working its way down. Tells us whether or not the tree has the given key. So if we get past the return statement, then we know that the tree does contain the key, and we call an erase node helper function. What erase node does is it's given a key that is definitely in the tree, and it goes in and takes the node for that key out. That's all erase node does. So erase node will do the work of finding a node, taking it out of the tree. After erase node finishes, we know the node has been removed. There's just two more details for erase. One is size minus minus to keep the size accurate, and return true to say, yes, we did just change the tree. So now let's look at that erase node function. From here on out, we're looking at private member functions. These are all private. They're not meant to be called by the user of our class. They're only meant to be used in this process here. Erase node is given a reference to a key that needs to be taken out. Erase node can assume that the key really is in the tree because the public erase function dealt with that detail for us. Erase node returns void. It doesn't have anything to report. It just does this task. And we break this down into two steps. First, we call find node, which is on this slide. Find node is given a key, and it finds the node containing that key, kind of like its name says, and returns a pointer to the node containing that key. So find node takes a key as input. It returns a node pointer as output. That's the argument to remove node. Remove node is given a pointer to a node and takes the node out of the tree. Let's look at find node. It's a relatively straightforward function. It's given a key reference to search for, and it returns a shared pointer to the node containing that key. So this is, this algorithm we've done a bunch of times where we start at the root and work our way down, going into left or right child pointers until we find the right node. So we start this where pointer. Where is a pointer to a node that's going to keep track of the location where we are in the search process. It starts at the tree's root, and we keep going until the search is over with. And there's two ways that the search can stop. It can stop if where becomes null because we went all the way down to the bottom of the tree to a leaf and kept going down and didn't find what we wanted, and where becomes null. Or the search can end if where is pointing at a node that has the key we're looking for. So as long as we need to keep searching, meaning as long as where is non-null and also where's key is not equal to key, we continue the search and we go down a level. So if the key we're looking for is less than where's key, where becomes where's left. That's go down and to the left. Otherwise, where is where's right, go down to the right. We know that key is not equal to where's key because if key is equal to where's key, the loop would have stopped. We wouldn't have got into the body of the loop. So this continues until the loop ends, either because where became null in a failed search or because where's key is equal to key in a successful search, and we return the pointer we got at the end of that process. keep in mind in erase node, we know that key is always present, so we know find node will always return a non-null pointer. It will always succeed in finding a pointer to the node that we search for. So the next thing is remove node. The only member function we haven't defined yet is remove node. We're going to look at that one next. Remove node is given a pointer u. U is a pointer to a node that is definitely existing in the tree. It's not null, and we need to take u out of the tree. We had a whole video describing this algorithm a couple videos ago. Here's the logic. We're going to rely on a private helper function called remove 0 or 1 child. Remove 0 or 1 child is given a pointer to a node that certainly has 0 or 1 child, like the name says, and takes that node out of the tree. So you're not allowed to call remove 0 or 1 child on a node that has 2 children. Remove node deals with that issue. So if use left is null or use right is null, then that says one or the other of u's children is null, or maybe both are null. So that means u has 0 or 1 children, and we can call remove 0 or 1 child and we're done. That's all there is to it. So if one or both pointers is null, remove 0 or 1 child does everything we need to do. Else, both child pointers are not null. The only way to get past this if is if u left is not null and u right is not null. So that means u has 2 children. There's a little bit of an obstacle. We can't call remove 0 or 1 child directly because u has 2 children. So what we do is that whole successor trick. We need to find the successor node of u and copy that contents up into u and then remove the leaf successor node. So the first part of here is finding the successor of u. Remember, the process to find the in-order successor of u is you go right once and then left until you can't go left anymore, because going right once gets us into the subtree of keys that are greater than u's key, and then going left as far as we can gets us to the minimum key among that set. So to begin with, w is u's right. W is going to point to the successor of u. So w starts out as u's right pointer. We know that this is a non-null pointer because we got past this if statement. And while w's left is not null, w equal w left. So that's just doing that zoom down the left pointers until we can't go any further. So this loop will stop when w is a non-null node that has no left child. So w is definitely a node, but it definitely does not have a left child. U set contents to W contents. Contents is the key value pair in a node. So U, the higher node, overwrites its key and value with the successor node's key and value. So that destroys U's key and value. So we've almost done all the removing work. There's just one detail that right now at this moment there's 2 copies of W's contents. There's one copy that we copied into U, and there's another copy in this lower successor node W. We need to delete out that lower successor node so that we don't have duplication happening. And we call remove 0 or 1 child on W. That does the work of taking out that copy node deeper in the tree. And by definition, W does not have a left child. Therefore, W has 0 or 1 children. So remove 0 or 1 child will work on W. The last private helper function we have to define is this remove 0 or 1 child function. And it's given a pointer to a node U that needs to be removed. Note, by the way, U could have been the U or the W in remove node. So remove node in the 0 or 1 child case calls remove 0 or 1 child on U directly, and in the 2 child case calls remove 0 or 1 child on W. So this U over here could have been the U, or it could have been the W in the previous function call. Okay, so we set up 2 pointers to nodes. One is called S, the other is called P. S is the pointer to the node that's going to take the place of U. It's going to be the pointer that fills the hole left by U. P is going to be the parent of S. So we're cutting out U, and P is whatever is above U, the parent that's now becoming a parent of S, and S is the node below P that's taking the place of U. So we got to work these out one at a time. The first thing we're going to do is figure out what S should be. So U could have 0 children or it could have 1 child, and what we want to do is if U has a child, then that 1 child takes the place of U. If U has no children, then null takes the place of U. So if U left is non-null, if the left child is non-null, then S is U left. Then, that 1 child is the node that's taking the place of U. Otherwise, S is U right. So U right could be non-null if you had one child, in which case S points to a node, or U right could be a null pointer if you had 0 children, but either way, that's the right thing to do. So after this if statement, S points at the one and only child of U if there is such a child, or if U has no children, S points at null. Now what we're going to do is update the downward pointer that points at U, and we're also going to figure out what the parent of U is in one if statement. So if U is equal to the root, this is doing a pointer comparison. If the address of U is equal to the address of the root, then U is the root. You can do that kind of pointer comparison. So that means the downward pointer that points at U is the root pointer of the tree. We reassign the root pointer of the tree to become S. That also means S has no parent, so P is null. The root has no parent. Else, that means U is not the root, so U is a child of some parent P. We calculate that parent here. P is U's parent. Just follow the parent pointer of U. And P is going to become the parent of S. But currently, P is the parent of U. And now we need to decide, is it P's left child pointer or right child pointer that needs to change to point at S? So we're filling the hole of U. The downward left or right pointer of P is going to skip over U and go directly to S downward. So if P's left pointer is equal to U, then U's parent is currently using its left child pointer to point at U, and we reassign P's left pointer to now point at S. Otherwise, P's right pointer is the one that needs to be reassigned to S. Okay, the last detail is we might need to update S's parent pointer. So if S is non-null, then we just set S's parent pointer to P. So these F statements figure out P. P is the parent of S after U has been removed. And the if statement is there because S could have been null. Remember up here, S is assigned to either a node pointer in the one child case or null in the 0 child case. We don't want to follow a null pointer down here by mistake. So if S is non-null, we say S set parent to P. And that's it for the removal code.